Professional software development requires absolute clarity when systems fail. In Python, an exception is a signal that something has gone wrong during the execution of a program. While Python provides built-in errors like value error or type error, these standard tools can fall short. Why? Because they are often too generic for complex business logic. To solve this, we use custom exceptions, which are user-defined error classes designed for a specific domain. Instead of a vague notification, a banking application can be programmed to raise an insufficient funds error. This immediately and clearly identifies the exact business problem at hand. This approach ensures that enterprise-grade software communicates failures specifically, providing enough context for engineers or automated systems to resolve the issue without playing a guessing game. To truly understand the necessity of these specific alerts, let's consider the analogy of a hospital emergency system. In a medical crisis, a generic announcement of a problem over the loudspeaker simply creates confusion and delays the response. No one knows exactly what to do or where to go. Instead, hospitals use specific codes mapped to specific responses. For instance, a code blue in ICU room 4 specifically alerts the cardiac arrest team. Similarly, an allergic reaction in room 12 immediately summons an allergy specialist, and a fire alarm in the West Wing triggers the evacuation team. Each specific alert ensures that exactly the right people are activated for that unique situation. Custom exceptions function identically in our code. By throwing specialized errors, they provide precise information to the specific part of the program capable of handling that exact failure. Now that we understand why these precise signals are so valuable for robust software, let's explore exactly how to create and build these custom exceptions in the next step. Implementing custom exceptions involves 3 fundamental steps. First is the creation of the exception itself. As you can see here on the left, we do this by inheriting from Python's built-in exception class. Even a minimal implementation, like just declaring the class and using pass, is a huge improvement over a generic error. Why? Because it gives our error a unique name that immediately tells us what went wrong. The second step is building a hierarchy. This involves grouping related exceptions under a common base class. For example, we can create a banking error to serve as a parent class. Then specific errors like insufficient funds error and account frozen error inherit directly from that parent class. This smart structure allows developers to do 2 things. They can catch all banking-related problems at once, or they can target one very specific issue. Now, the third step makes our exceptions truly powerful: attaching context data. Instead of just returning a plain text message, we define an init method within our custom exception class. This allows us to store crucial details like the specific account ID and the transaction amount right on the error object itself. By storing structured data this way, we make it incredibly easy for logging systems and dashboards to extract the information for fast debugging. Let's look closely at the exception hierarchy diagram to see a visual representation of this structure. At the very top, we have the Python built-in exception. Right below it, we establish an app error class, which acts as the base for our entire application. From there, it branches into 3 main domain categories: banking error, inventory error, and payment error. If we look under banking error, we find our highly specialized cases, like insufficient funds error, which triggers when a balance is lower than a withdrawal, and account frozen error. The beauty of this hierarchy is that you can catch errors at any level. As the code block on the right demonstrates, catching banking error automatically handles all issues in that entire branch. But if you need more precise control, catching insufficient funds error handles only that specific scenario. So the key takeaway is that custom exception hierarchies transform generic crashes into rich, structured signals that make your application much easier to maintain and debug. As we move to the next slide, we'll see exactly how this structured approach is vital for managing complex risk validation in real-world trading platforms. Now that we know how to build a custom exception hierarchy, let's see why this is absolutely critical in the real world. In the banking, financial services, and insurance sector, specifically when we look at stock trading platforms like Zerodha or Upstocks, custom exceptions are the backbone of their risk management. When a user clicks buy or sell, that trade doesn't just happen instantly. It must pass through multiple strict validation layers. Each of these layers uses very specific custom exceptions to enforce boundaries and instantly block bad trades. Let's explore some of these domain-specific exceptions shown here in the middle. First, we have the market closed error. This is raised exactly when a trade is attempted outside of active market hours. Instead of a generic operation failed, the system immediately knows the market is shut. Next is the insufficient margin error. Think about what a platform needs to know when rejecting a trade for lack of funds. This specific exception is designed to capture precise data points, the required margin on one side and the available margin on the other. It explicitly tells the user and the system exactly why the trade was blocked. Then we have the position limit exceeded error. This tracks when a trader tries to hold more units of a stock than they are legally allowed to. And crucially, the instrument suspended error identifies when trading on a specific stock has been entirely halted by regulators, such as SEBA. To make all of this manageable, these aren't just random standalone errors. Look down here at the bottom. They are built into a strict exception hierarchy, all inheriting from a single base trading exception. This structure ensures perfect alignment with strict SEBI and exchange regulations. A fantastic practical example of this is the Zerodha Kite platform. When an order fails on Kite, it triggers an order rejected error. This doesn't just say failed, it actually carries the precise exchange rejection code and the detailed reason right inside the exception object. Similarly, the risk limit breached error automatically captures the trader's current exposure compared against their specific hard limit. So what is our big takeaway here? By using custom exceptions to carry rich, highly structured context, platforms can feed real-time risk dashboards that monitor millions of traders simultaneously without losing critical details. This exact same architectural pattern of capturing context in exceptions isn't just for finance. Next, we will see how a massive retail inventory system like DMart uses these same principles to track stock. Consider a retail inventory system for a chain like DMart. The implementation begins by establishing an exception hierarchy. The inventory error class serves as the base, inheriting from the standard exception class. Its initialization method accepts a message and a store ID, ensuring every error knows exactly where it occurred. From there, subclasses like ProductNotFound and OutOfStockError extend this foundation. For instance, notice how OutOfStockError captures the product ID, the product name, the requested quantity, and the available quantity. This level of precise detail is critical for automated replenishment systems to function properly. Moving to the center, the product class represents individual items. It intentionally uses private attributes for price and stock to ensure they are only modified through validated methods, protecting the integrity of the data. To manage these products, we use the inventory system class. It includes an internal helper method, getProduct, which checks if a SKU exists. If it doesn't, it raises a ProductNotFoundError. This cleanly centralizes our error checking so that our main functional methods stay uncluttered. Let's look at those functional methods below. The sell method performs necessary logic checks. It ensures the quantity is positive and verifies that enough stock is available. If stock is insufficient, it raises the out-of-stock error with full context. Similarly, the replenish method checks if adding stock would exceed the warehouse's maximum limit, raising a stock replenishment error if it does. Finally, the update price method enforces business rules, preventing accidental price drops of more than 50% by raising an InvalidPriceError. When testing these execution paths, the use of try-except blocks allows the system to handle failures gracefully. If a product not found error occurs, the system can print the specific bad SKU. If a stock replenishment error triggers, the system knows the exact capacity gap. Ultimately, by catching the base inventory error, developers can easily catch any error within this entire inventory branch using a single block of code, which is the true power of an exception hierarchy. Understanding the structure prepares us to distinguish these domain-specific exceptions from built-in types, allowing our logging systems to record exactly why a business rule failed rather than just recognizing a raw data error.
Following up on that inventory example, let's look at how to truly master custom exceptions by distinguishing them from built-in types. For example, if we just use a built-in value error, it only tells you a number was wrong, but a custom insufficient funds error tells you why it was wrong in a business context. This is absolutely essential for creating better logging and automated customer alerts. Also, notice the important difference between simply using raise, which starts a brand new error, versus raise X from Y. We use exception chaining to wrap a low-level error into a meaningful business error, preserving the original cause. To put this into practice, let's design a flight booking system. This requires establishing a booking error base class. From there, we build out a specific hierarchy. We create flight not found error when a flight doesn't exist. We use seat not available error, which carries context like the requested and available seats. We also add invalid passenger error for data validation, payment failed error with transaction IDs, and cancellation not allowed error for timing violations. Down below, we outline the classes to build. These include flight, passenger, booking, and the main booking system. This system must implement methods for adding flights, booking, and canceling, properly raising those precise errors we just defined in the hierarchy. Now, let's summarize the 4 rules of professional exception design. First, Rule 1, build a hierarchy. This pyramid structure allows you to catch errors at different levels of specificity, falling back to a base class when needed. Second, Rule 2, attach context data. You should include things like amounts, transaction IDs, and specific reasons directly to the exception object, not just hidden away in a message string. Third, Rule 3, name with domain language. For example, insufficient funds error makes far more sense in a banking application than a generic value error. And fourth, Rule 4, one exception equals one problem. Instead of throwing a generic app error that gets reused for unrelated failures, create specific exceptions so you always know exactly what failed at this location with these specific values. By moving away from generic Python errors and implementing a structured hierarchy of custom exceptions, you completely transform how your application handles failure. You move from a confusing something went wrong state to knowing that exactly this business rule was violated at this location with these specific values. Following these rules empowers you to build robust logging systems, clear user-facing alerts, and sophisticated error recovery logic that makes your software truly resilient and professional.